started talking about USB. So that is the universal serial bus. So this is a layout of USB that we are talking about. So there we have seen that there are mainly three main modules present. One is a wrapper, one is a controller, and one is the PHY module, or you can tell this one is the basically the physical module, which takes care of translating data to its suitable USB form. You may, okay, 1 second. You started the recording, right? Yes. Okay. So now we will see what are the steps associated in USB data transfer. So yeah, maybe you have observed already few terms. This is pipe. This is the pipe. This is the DoD controller. So today we will define properly these few terms and we will see how these are associated with the data transfer. Okay. So when we are talking about USB data transfer, of course, you know, one device is attached to USB. Maybe that device is requesting data from USB, or it is transferring or storing some data in USB memory. So whenever a device is attached to the USB system, it gets assigned with a number that is called address. Now, whenever a device is getting attached, the whole device may not be communicating with the USB. Maybe some part of that device is actually communicating through the USB part. So that way, each device contains a number of endpoints or the buffers. These endpoints are mainly responsible, or they are actually acting as main source or destination when the data transfer is taking place. So of course, that is our endpoints operate in simplex mode. That means they are either an input or working as an output. Okay. Now we are coming to, okay, next one is the pipe. The pipe you have already seen in the layout. This is simply yes.
Ma'am, could you please explain in details about the endpoints?
Yes. Okay. We will take one example, then I can explain. Or okay, maybe you think in this way. When a device is connected, okay, maybe your keyboard that is connected, but when you are from your keyboard, maybe when you know that with your system, with your PC and your keyboard, that is basically a USB connection. USB communication is taking place, but it is obvious that the whole keyboard is not actually communicating with the PC at a time. Some particular keypad that is communicating with the PC and that is sending the data to PC, some input or something like that. So in that case, that particular keypad or buffer associated to that keypad is your endpoint, and your device is the keyboard. So that way, the portion or the particular area of your device is related to that data communication, maybe data output or data input or storage. So that particular portion we mention as endpoint. Is it clear now?
Ma'am, here device is the computer or keyboard you are saying?
Device, you are thinking about the keyboard.
Okay.
Okay. Okay. And the key associated with that keypad, a particular keypad associated to keyboard, you can think as an endpoint.
Well,
Okay,
if I
okay,
type, let's say A in the keyboard, so A will be my endpoint.
pardon?
And if
Can
I
you come?
am if I am giving the information of A in the keyboard to the
Yes,
computer,
yes,
so
yes.
the
Mhm. Yes, correct. That is one endpoint. So that will vary device to device, and based on the device, your endpoint can be different. Will be different. Okay.
okay, I'm going.
Okay. Next one is the pipe. Pipe is simply the data path that is between an endpoint and the controlling software through which the connection, I mean, the communication is taking place through this data pipe. So you may see when we have talked about here, that's why this communicating path, it is mentioned as pipe. Okay. Especially in case of super speed USB, these terms are associated. Now we talk about the types of the data transfer present in USB. Now, there are 4 types of data transfer: control transfer, isochronous, interrupt-based transfer, and bulk transfer. Now, as the name suggests, these control transfer is for configuring or controlling. Okay. When the host, which is interested to initiate that data transfer, actually speaking, USB always works in a master-slave mode. Like there will be one master, one host that is initiating the data transfer. That may be from host to USB or USB to his host, but mostly host is initiating and acting as the master. Okay. So that in that way, the host is taking the control to USB and checking whether data transfer is possible or not. And if USB device is ready and everything is matched, then USB device will send one acknowledgement signal, that followed by that acknowledgement signal, next level actual data transfer will start. So this is the initiating portion, initiating control transfer. Okay. If there is no control transfer is unsuccessful, then of course host will not receive back any acknowledgement. This acknowledgement signal will not receive back, and it will maybe start the second attempt, third attempt, in that way, that to again start initiate the transfer. Next one is isochronous transfer. This involves data where accuracy is not critical, but they are sometimes mostly time bound, or they need to transfer at some constant rate, like audio or video data, real-time process data. So these are isochronous data. In this case, you can see the host will transfer the token of data transfer. I mean, initiate the request of, we will see what exactly mean by token transfer, but initiate the transfer to USB device, and then the isochronous communication will take place. Next one is interrupt transfer. These are small infrequent transfer, and this is determined whether this interrupt handling is required or not. Here, this is determined by polling technique. Now, the endpoint that tells the host that when the polling is required, or not when, I mean, in which duration or which interval, we should say, the polling is required. Polling means at that point, the main host will check whether any interrupt is required or not, or interrupt handling is required or not by the endpoint. If so, this data transfer will be stored, and interrupt always is with high priority. That interrupt signal will be processed, interrupt task will be processed, and after that, USB data transfer will take place. Okay. The next one is the bulk transfer. Bulk transfer, of course, the internet we mostly do with USB. Whenever you are storing some data to USB, or you are taking back the data, again the same method. Host is sending the initial token, and if it is for input transfer, then the data requested from the USB will be taken back by host. We will see in which form, how the USB will understand which data to send it back, etc. We'll discuss one by one. But thing is that the host will initiate with this input token or output token. Output token means now data will be sent from host to USB device, and you are whenever you are acting, I mean you are using that USB device as storage maybe, or some other requirement also. You are sending some input and you're you're sending some input to your device, USB associated device as an output. So in those cases, mostly you are sending out or some data to your USB device. So for that, output token will be sent, and then data will be immediately sent, and then USB device will send that handshake, that is the acknowledgement that yes, I have received the output token as well as the data. Okay, so this is for the bulk transfer. But the important thing is to note that this bulk transfer is with lowest priority. So whenever any USB connected device that is heavily loaded, that means that is associated with some other interrupt transfer, associated with some other isochronous transfer. Of course, controls transfer is the initiating part. So maybe some other isochronous transfer or interrupt transfers, if they are there, then bulk transfer will be stalled or they will be assigned relatively slow speed. So this is with the lowest priority, because generally we make bulk transfer either to store data or to retrieve huge amount of data when we are using USB as a storage. Now, this is what type of data this USB pipe is actually allowing to transfer. Next question is how this data will be sent or received in USB. Now, you remember last day we were just looking into this part. Also, this is the USB memory part. So, whenever you were some request is coming, somehow some address mapping should be there, by which data will be taken from this RAM part of USB or will be stored in this RAM part of USB. Okay. So now the question is, we will see how this, in which form this request is coming and how USB is actually understanding that request. Okay. So when the software requests data transfer to occur, it sends a block of request. that is we call IO request packet. So again, the request is coming in the form of IO request packet. The last day we were mentioning the same thing in the USB point of view. When remember in this right, that the request comes in form of multiple transfer request blocks. That is the same thing we are talking about, this IO request blocks. They may come in a single or multiple way, but they are processed in single string with a serial communication. We will see today that. And if there is an error, then all other next subsequent request blocks get stalled, this error get resolved, and then USB takes the next level processing. So now just come to this. Yes. So now USB is receiving this IO request block. Okay, and this part we have also mentioned last day, that software is later notified when this request is completed. That means, go back from the USB's point of view. Here we check each TRB has one hardware own bit. Based on that is set or reset, it is notified that whether the whatever request came from the host part, whether that is processed or not. Okay, so this is the hardware part of USB, which shows the indication whether a particular request has been processed or not. Now coming to this part, Now USB is getting that request, as we mentioned, that is this IO request block. Now, what does it mean, IO request packet? This is a typical, the communication takes place in serial form, and this is the packet structure. What is there inside the packet? This is again the 8-bit for synchronization. This is the PID. This is the packet identifier. Now this packet identifier is of 8 bits. The first 4 bits that contain some information. We will talk about that. What does it mean by what we mean by this initial 4 bits? And the next 4 bits are just the complement of those bits. This is basically one sort of error check. That means if one bit is modified, I mean, maybe you are sending this value 111010. That means in the next 4 bit 0101. So if in the receiver side there is a mismatch, of course receiver is expecting whatever bit here, just the reverse bit in the next 4 bit. So if any bit or any subsequent bits are flipped or changed due to some communication error, but the equivalent bits, the flip bits or the ones complement bits in the next 4 bits, if they are not changed, then receiver can understand that there is a possible error. So this is the error checking method, method that is used in USB communication. Okay. Now, what type of information PID controls? Those are mainly, they determine the type and the format of that packet data. We mean by type of packet data, these are 4 types possible. One is the token packet. So this token packet is basically, again, this is just to query the device, whether that is the initiating part, that is whether the recipient is ready to send or receive data or not. Remember, when we are talking about these communication, that's why we have always mentioned the first communication with initiating tokens. Maybe it's interrupt token, maybe it's input token, whatever it may be, types of token that is indicating that what type of transfer it is. And this token is actually basically a request to initiate the communication. Next one is start of frame packets. The start of frame packets, again, that is that will indicate again for synchronization. I think we have discussed about the start of frame bits also in our previous discussions in previous different protocols. Next, the actual data packet consists of all the above field types. And next, the handshaking packets. Handshaking packets mostly used in this acknowledgement part. You can see these are handshaking packets when that is a confirmation coming from the USB device end to the host end that the whatever request was there, it was processed. And we know that from our previous layout information, then at that time USB basically sets that HWO, hardware own bit of a particular request block to 1 or 0, set or resort. Based on that, it sent the USB sends this handshake information, that is the acknowledgement back to the host that whatever request was there, that was processed. Okay. Now, so this is the sync field, the PID, that is giving the type of data, type of request that is sent. Next, this is the address. Again, the address related to the function or the endpoint with which the communication should, address is the address with the device. And then associated with the address, we are adding this endpoint address. So together, for a particular address, associated address should be the endpoint address, and together this whole field is actually describing what is my destination or what is my source from which data will come, or what is my destination endpoint buffer. And this is the data part. Data, of course, this is a specified byte limit in the USB protocol, that this maximum amount of data you can send in one packet. So while in bulk transfer also, we are dividing this data in these form of packets, and the communication is taking place. So this way, now if you go back to this hardware, this layout, you understand this. When we talked about this packet based communication strategies, the controller is this one. And what type of, whether it is an interrupt relation, whether it is a initiating the control transfer, this part is communicated by this wrapper. And this HY layer, this is for modulation, demodulation, serialization of data, and the final communication. Basically, this defines the physical layer activity. Okay. So this is the few steps how data communication takes place in USB with these 4 modes of transfer and with these form of data packets. And of course, in this with the form of packets, you understand this occurs in a serial form of communication, when the least significant bit is kept first and then followed by the most significant bits. Okay. So this is the steps of USB communication, basics of USB communication. So do you have any question on this USB part? Do you want me to repeat any part? No, right?
It's clear, ma'am.
It's clear, right? Okay. So this is the basic of few communication protocols that we have discussed, starting from UART, SPI, I2C, and then at last with USB communication. Now you see, whatever we have discussed so far, that is mostly the aspects of data link layer and also the physical layer clubbed up together. Because physical layer means when we mentioned about the OSI model, we talked about the physical layer, which is defining the bit level transmission. That is how the bit sequencer are communicating, what are their synchronization techniques. All these things we have mostly discussed in these protocols. Mostly whatever information we have talked about so far in the context of embedded networking related to physical layer and data link layer. Now today we will be talking about a bit the actual embedded networking, when we will be talking about the routing concept required in, and what are the routing challenges when we are actually going for embedded routing. So maybe before going to the embedded routing, just a quick recap about what we know about our routing concept in our, from the general traditional networking, from the concept of internet. So you understand that when we have our home network connected with multiple hosts, and when we are trying to connect them to the internet, basically they are going through some router. Router means what? Maybe maybe a connector you can think, which is containing some routing algorithm. Routing algorithm means your network is very fast when multiple LANs are connected, multiple local area networks. Local area network means few nodes are connected to them. Now, when you are trying to connect few multiple LANs, so from going when and you are trying to communicate from one host to another some destination, the path may be through multiple such LAN networks. Now, what or which way will be suitable? Which way will take least time or least terms, least cost in terms of maybe some other metric that is defined in the router part. Okay. So before that, we were here, we have talked about when we are getting some data from application. This is just JSON data we are getting. Now it is ready for transmission. And for that, first we need to check in general concept of transmission that how port to port communication can be established. Now this port to communication and synchronization, that client and server, both whether both are ready for communication or not. So that is taken care in this transport layer. And when we are generally defining this TCP/IP protocol, we know that at the core of this, we have two typical protocols. One is TCP connection, TCP, and one is IP. TCP or UDP, it may happen that it is basically between client and server connection, creating the client and server connection, what we are talking in TCP. That may be through some handshaking. Handshaking means client is sending some request, server is acknowledging, and server is and then the data communication is actually taking. Now, these type of connection establishment is taken care in this transport layer. And then we are coming to this IP layer, where my IP data is basically taking the data, taking the input from transport layer, and on top of that, we are adding the IP header. And actually, this is the concept for each layer of communication protocol, where we are getting whatever input we are getting from the previous layer, we are just adding some header associated with that. Now, of course, when you are adding that header, that means we are adding some extra information. Now, you can observe when we are adding the data, let's say this is my application data. When I'm passing that through my transport layer, I'm adding the information about the source port, destination port. Okay. So rest are checksum and all, they are just for communication purpose, they are for error detection, correction, everything is fine. Then from this TCP, from transport layer protocol, we are coming to IP, where this whole thing is acting as the data. And on top of that, we are adding some header that is giving the idea of my source IP address, from where this data, from which IP address my data is coming, from which destination address my data is going. So this is the flow, the concept in throughout the OSI or TCP/IP, whichever layer you consider, that you are taking the data from the previous layer and you are adding some header. Header means some extra information based related to the main purpose of this layer. Like for transport layer, it is port to port for communication. That's why we are adding port address. For network next layer, internet layer, or here basically whatever we call in network layer in OSI model, here we call it internet layer. So we are adding the source IP address and destination IP address so that we can actually mention where this data will be going. Now for IP layer, there are two concepts, two main purpose. One is creating this datagram, adding suitable IP address, destination address, so that this data starting from that, from a particular source can reach to its destination. Or if we want some acknowledgement back, then it can come back to the source IP address. And next one is the routing protocol. Routing means like your LAN, maybe LAN 1, LAN 2, and so on. These are connected. These are connected. And from LAN 1 to LAN 5, you are interested to send some data from, but you have to know that which path is suitable enough or cost effective to follow when you are sending your data from one LAN to another LAN. So that is defined in the routing protocol or the routing algorithm that is present inside the router. That means your LAN is actually connected to a router okay, in between router. This router is actually running some algorithm, is storing some table that will give you the idea whether the data coming from this LAN, whether it will go to this path or it will go to this path. Now that defines your routing algorithm or routing protocol. Now this routing protocol can be of two types. One is adaptive routing, that is dynamic. Of course, that we are interested in. And another one is static routing. One form of the static is flooding. Flooding means what? Let's send that information to each and every IP address. Whenever you are trying to find a particular source, a particular destination address, destination IP, let's flood the network with your packet, and your packet is containing the particular destination address. Each node will check whether it is getting a match with your destination address, it will accept, otherwise it will reject that. In that way, somehow your packet will be delivered to the destination. Another one is random walk. Random walk means you just send your data randomly. Just allow your packet to take some random path, like from LAN 1 randomly it can choose to LAN 2, then maybe this path, then this way somehow this version, your packet will be delivered to the final destination. In spite of the fact that we do not follow or we do not consider this type of non-adaptive routing in a larger way, basically mostly we follow this dynamic adaptive routing, but we will see whenever we are designing any dynamic routing in a smaller part or in a part of this, as a part of this dynamic routing concept, somehow we will be using this type of flooding or this type of static routing concept also. Okay. So based on that, adaptive or dynamic routing can be classified into three product categories. One is centralized, one is isolation based, and another is distributed. As the name suggests, from the name I think you can understand that centralized means somehow one central node is there, or the whole computation of proper routing algorithm can be taken care of the knowledge of the full network. So in case of centralized routing, that whatever knowledge we require, that is related to the full global knowledge of the network. On the contrary, as the name suggests, in case of the isolation algorithm, what happens? We obtain the routing information for a smaller part of the network, which that we can consider as some local information. And based on that, we proceed to get the actual routing, we proceed to form the actual routing table. In distributed algorithm, what happens? We need to have the information between a particular source and destination, and we just extend that information in an iterative way and then find the whole view of routing algorithm, get the whole idea of routing table. We just develop the routing table. Now, it is the three typically separated idea, and in our case, when we are more concerned about this embedded networking or embedded routing, we are not going in the detail of each of them, because under every category there are different algorithms. You can see here under link state there are these algorithms. Under distance vector, when we are talking about this distributed algorithms, distance vector, path vector based, there are different types of algorithms. We are not going to talk about that. What we are interested, we will be talking in detail one algorithm, that is optimized link state algorithm. Because when we will be talking about embedded scenario, we will see, if you take any example of embedded networking, that is mostly prominent in CPS or IoT scenario. Now think the like vehicle to vehicle communication, where you have to consider some network that is ad hoc. Nodes, location of the nodes are continuously moving. So some ad hoc network, some mobile ad hoc network we have to consider. And not only that, along with that, we have to consider some, where is that? Okay. We have to consider some sensor associated with it. So whenever we are talking about this embedded routing concept, we have to actually consider both the concepts. In one hand, that mobile ad hoc nodes, mobile ad hoc networks, and in another concept is the wireless sensor network. So here in this embedded routing, we will basically discuss in detail typically one protocol that is the amalgamation of two protocols. One is from this optimized link state algorithm that is heavily used in mobile ad hoc network, and another algorithm that we will discuss later that comes from the concept of wireless sensor network. And because whenever we are thinking about this type of embedded networking, embedded routing, we have to think this CPS or IP scenario. Let's say this V2V communication. That means you have multiple vehicles. They are communicating with each other, and their locations are getting changed. They are associated with some sensors. So wireless sensor network and mobile network ad hoc network, both the concepts should be connected together to basically understand this embedded routing. Okay, and along with that, whatever protocol we will be choosing, that should be adaptive to battery power, and also that should be adaptive to changing network topology. That is very important, and that is not so important in case of in general our general internet concept or traditional communication concept, because when you are actually proposing a network, proposing a topology there, topology means how the nodes are connected and how they are forming the LAN, from there how they are actually moving to the network, how the routers are connected. These are more or less stable. It is not that after a few seconds, it may change. That requirement is not present in our traditional routing technique. But when we are moving to this embedded routing, these type of V2P communication, sensor-based network, IoT framework, this adaptivity of this changing network is very important. That's why we are trying to mingle this concept here. That is the concept of mobile ad hoc network, concept of wireless sensor network, and together the amalgamation of those can form a suitable embedded routing protocol. Okay. So when we are talking about mobile ad hoc networks managed, so that is again the same thing, that is self-organized. Each node acts both router and the host. Okay, multi-hop, distributed. So all these features are there. Dynamic topology. Now from these features of MANET, you can understand why it is so close to our embedded networking requirement. And also another thing is that lightweight terminals. Whenever you are choosing any algorithm, it is better if you can have it as lightweight as possible. The reason is, the more costly it will be, the more cost you have to support in your resource. In resources, I mean computational resources present in the node itself. So that's why since they have lightweight terminals, so your algorithms also should be chosen in that way. And shared physical medium, I think this one we have already discussed, and we know what are the challenges in that and what solutions to adopt in this scenario. Okay.
Ma'am,
Yes.
hello. Ma'am,
Yes.
please explain this in the previous slide.
Which one?
In the previous, yes, ma'am, multi-hop routing and this dynamic topology, both better.
Okay. Dynamic topology is like, okay. See, if you think about your traditional communication, okay, traditional internet. Internet means what? Your nodes, some systems connected to some long wire, they are forming the LAN, and this LAN through some router, it is getting connected. Again, some LAN maybe the nodes are arranged the same way, or maybe in star topology, there are topologies may be different, but more or less these type of LAN, I mean arrangement of LANs or nodes associated with those LAN and in turn to the whole network, it is constant, right? There is not much change in that. Sometime you are adding some node, sometime you are deleting some node, so there is not much change. But you now think about the scenarios where we are interested in, where embedded communication is mostly prominent, like your V2V communication. In V2V communication, what happens? You have multiple cars in the road. They are moving. After a certain time, their location is changing. Their speed may change. Distance between them may change. And when they are moving, maybe when this car is here, maybe this C1 is here and C2 is here. When they are proceeding to the next location, maybe there are some traffic signals. So runtime, that signals should identify this car and that should send their message. I mean, message about whether to stop, whether the signal is green or blue. So when everything is sensor based, you have the challenge that how this dynamic location of your car and how it is actually interacting with the other sensors present in the environment you are considering. Clear? So the topology is dynamic, it is continuously changing, and you have to adapt. I mean, whatever environment you are proposing, that environment should adapt these changes quickly. There is, if this, the signal, I mean, this sensor is, I mean, there is a significant delay in reacting to this change. In reacting to the fact that these cars, maybe 5 minutes ago, maybe 5 seconds ago, this car was not in its environment, but now this car entered into its environment. So that means this topology is dynamically changing and constantly changing, and all the components in that network should adapt according to that. And that way it should plan or design its path. Okay, so that is the dynamic topology. Then it is multi-hop routing. Multi-hop routing means, okay. Multi-hop routing means you are having one LAN. Sorry. You are having one LAN. You are one router here. Then you are intended to go to some destination in some LAN here. Okay. Now this path may come to a single router, or maybe, and this router, based on the path cost, we will actually discuss about that when we will take the example of that link state algorithm. This router will actually think, no, this part is more costly, maybe cost associated with this path is 6, and if I transmit that to another path, maybe here this link cost is 3 and this link cost is maybe 2. So that means the cost of overhaul in this direction, the path cost is less. So this allows the multi-hopping, that hopping from one node to another, and then you are actually taking the least cost path. So that is the concept of multi-hop scenario. So that we will also talk about this. We will take the example of how to calculate the cost of this multi-hop routing and all. So there we will see this, all these features you need to consider in your mobile ad hoc network or in your embedded network also, where the requirement is changing in an ad hoc way and new nodes are always getting added, or some nodes are getting deleted from your environment, and that change number of nodes, change cost of nodes, change presence of node, everything you have to consider as your full environment, as your full network. Okay.
Yes, ma'am. Ma'am, what is the real life example of this mobile ad hoc network?
This is, see, in embedded scenario, whatever I have told, this B2B communication, that is also one real life example, right?
Okay, ma'am. So, ma'am, for facing this.
Yes. Yeah.
Yes, ma'am. Yes, ma'am. What are you telling?
Yeah, I was telling that whatever example I have given, that vehicle to vehicle communication. Then when this one vehicle is basically determining where is the next vehicle, or what is the distance of the vehicle in front, or what are the pedestrian associated with, that from their inputs that vehicle should consider. What are the sensors, maybe traffic light sensors or other road sensors present. So those are constantly changing, right? Whenever you are thinking about a network, after 5 seconds it is getting changed, because your car is moving, and while moving, all the associated sensors, pedestrians, your front car, back car, everything is changing. So if you consider each of them as a node, so of course this is your some ad hoc network where nodes are mobile, or you can consider your your mobile as a node in terms of communication, right? What is the fundamental concept of mobile network? That is, you are moving, the person with whom you are communicating, he or she is also moving. That is changing, and somehow there is some base service pointer, we say. From there, this service points get connected, and that base service points also get changed, and that communication, the base service points, they consider these nodes but after some time, maybe some node is getting deleted from their network and some new node is getting added. So the changing and adding of those nodes are constantly, rapidly changing. So that is the requirement here, and that is the challenge here. Okay.
Yes, ma'am. Got it.
Okay. Okay. So in case of managed routing protocols, we have different types of protocol. Again, that we told about this topology based, location based, and also another important thing is that is energy awareness based. That means that routing should be done. Routing means the path from source to the destination that is getting selected. That should be selected assessing the power levels of the network nodes. Okay. Now, routing table, okay, what I will do once I will discuss about this one example with that link state algorithm, then maybe it will be clear for some of you that how this routing level is getting associated and what does it mean. Routing level means it is storing the information based on some metric, like from A to B, if I should take a direct path or I should take one another path considering one intermediate node from A to C, then C to D. So based that cost, whenever I'm calculating, then in case of our embedded scenario as well as managed scenario, we should consider in this case the energy awareness of that node. Otherwise, that is related to depth of nodes. Maybe that is more prominent in wireless scenario also. So what we were talking about when we are talking about this embedded network, we are mostly interested in mobile ad hoc sensor network, where we will consider both this mobile ad hoc network as well as this wireless sensor network, where each node is basically related to handling sense data, temporarily storing it, and transferring the sense data to another network. Whereas this wireless sensor network is normally a centralized network. Along with some centralized framework, we need to incorporate this ad hoc realization. Okay. So that is the challenge, and that we will see in maybe we will start the next day, that how we are trying to mitigate this, that when we are talking about a wireless sensor network, we have some centralization in picture, and along with that we have to actually adopt this ad hoc node addition and node deletion requirement. That way we can form actually this embedded networking overall infrastructure. Moreover, when we are talking about this wireless sensor network challenge, the sensors, what they do, they always transmit their measured data to some sync node. Maybe that is their centralized node. And the lifetime of this wireless sensor network also related to the power associated with each and every node, because low or empty batteries of per node, they are related to the date of sensors. So whenever we are basically choosing some routing algorithm, here my cost is not only about only the distance between one node to another. We have some other features to consider, that is power, that is lifetime of that node. Everything should come into picture, and together that will form this mobile ad hoc sensor network suitable for our embedded scenario. So maybe next day we will start with this link set algorithm, basics of that, and we will move to and we will see what optimizations we can actually make, that it can make something lightweight, and it is optimized enough to be suitable in this managed and managed sensor network routing. Okay, maybe next day we will start, because it's already 6. Fine. Anything you want to ask? Next day we
No,
will
ma'am.
start about the, yes sir. Next day actually we will start the exact algorithm, the routing algorithm that is suitable for both this MANET and I mean combined wireless sensor network as well as this embedded scenario. I mean with the ad hoc requirement that is suitable for this embedded scenario. But I hope now you understand what is the requirement, why our general purpose routing algorithm or routing idea, it's not cannot be adapted as it is in our embedded scenario. Okay, so that's all I think for today. Thank you.
Thank you.
Thank you, ma'am.